Hey Sandeep, doing good. How about yourself?
Good, very good.
How's
And
your weekend going so far?
weekend is good. Weekend is good. Weekend is good. And wonderful, wonderful. Where are you based out of?
Sandeep, right now I'm in India, in Kerala, but generally I frequent between Kerala and New York. It's because, like I told you, right, I got my ACL injury and multiple ligament injuries. So I'm just like here for the next 2 or 3 more months
Where,
before I
where,
fly back home.
where are you?
Specifically in Ernakulam in Kerala, India.
I know.
Yes.
Kerala is beautiful. But it must be hot now, right?
It's like actually it's not too bad. It was hot, I think 3 weeks back, really hot. Now
Okay.
it's like monsoon, so it's very sunny or very humid. One of
I see.
those two.
I see.
That's how it is.
I see. I think we were there in 2021, February or something. Okay.
Oh, okay. Where do you guys visit?
It was Kochi. So I was living there for a month. It
Okay.
was nice. Beautiful.
Did it
Beautiful.
just come for a work visit or?
So see, with the CloudxLab, right? I have always been, I never wanted to have an office. My teammate wanted to have an office, so I had taken an office in Bangalore. But then before COVID, we vacated it. Then, right? So I
Oh,
always so once we just went, I just went and lived in Goa for some time, a month. Okay.
very cool.
And then before COVID, okay. So yeah, the work from anywhere has been going on for me for quite some time.
Nice. Yeah, yeah, Kochi is like pretty much where I stay. My
Yeah.
city is specifically called Ernakulam, but it's Kochi,
Yeah.
is what it
Okay.
is.
Where in Kochi? Oh yeah, Ernakulam was that place, all right. It's a,
Ernakulam is just a district, but the
yeah.
whole place is pretty much called Kochi.
Yeah,
So
yeah, yeah. So there is this drive. It's called very cool places.
is
Just
it
on
like Marine Drive? Where
Marine
like
Drive. I was living on the Marine Drive. Prestige.
yeah, Marine Drive is very beautiful. It's pretty much just like 15 minutes. That's where I go to have some tea with a view.
Yeah. So there is a building called Prestige something. I
Oh
was
yeah,
living.
yeah, Courtyard, Prestige Courtyard.
I think so. Yeah, yeah.
Uh,
So, it is
I
very.
see, I see. Yeah, yeah. I know friends who stay in Prestige Courtyard. I actually been in Prestige Courtyard multiple times. It's a
Yeah,
really nice apartment also.
yeah.
Like the families and everyone is really nice.
So for me, that experience was good. I think those who don't know, in there in Kochi, right? So the apartment's balcony opens to the sea. It's like backwaters, and it's like beautiful. And and so people had car parking and then boat parking. So some people go for walking, and some people go for kayaking in morning. Yeah, like.
You could see like all the even the harbor boats crossing by. A lot of people fishing over there. It's a really
Yeah,
nice view.
so the view from our balcony was like there was a fishing net. Then there was
Mhm.
this family who used to come and fish and every day, like very memorable time.
Yeah.
Very memorable time.
Well,
And
now you know a person the next time you visit in Kochi. So just if you're here, whole family is here. So you can pretty much hit me up anytime.
oh yeah, now I remember the Ernakulam was the district. Yeah,
Yes,
yeah.
correct.
All
Ernakulam
right.
is the district. Exactly. But
Yes.
everyone knows us like for Kochi. Like if you say Ernakulam, not much people know. But if you say Kochi, it's like, oh, Kochi, yeah, definitely. Water views, nice weather. So, but
Yeah.
yeah.
And cool, cool. So everyone, hi everyone, keep your cameras on. Make it feel like a class. And yeah, yeah, all right. Hey Subodh, how are you doing?
I'm good. Thanks.
Yeah, good. Yesterday's session was good. Class was good. I'm very happy that most of you have actually worked on the problems. And I'm happy that some of you have actually solved the quick sort. Okay. And so, yeah, in programming, right, knowing, right? So very, very important. I'll just open the Jupyter notebook and then I'll just start noting down there. Okay. Did anybody, you know, prepared questions from all? I was thinking that I'll sit down and today that, you know, I'll basically just create you know, I'll sit down and create these exercises. Okay, but there's just too many things to do in here, you know, groceries and all of that. There's just too much work here. In Canada, it's just too much of work.
There are a lot of
Very
things.
true.
There are a lot of
outside,
things.
That's the life outside. You can't do. I mean, in India, yes, a lot more comforts are there, and here, I mean, outside India, you just have to do everything by yourself.
Yeah.
Either you
We
can
take we
order
take
outside food, otherwise, yeah, just
we
keep
take a lot of
buying.
things which we get in India.
Yeah. I
Sorry.
it
Yeah,
was
we take a lot of things which we get in India for granted. Then once you come to US, Australia, or Canada, or any other place other than India, then you realize you have to do everything.
yeah.
Everything in the sense, everything, right? You
Except
want to wash your car?
except for Singapore. Yeah.
Mm.
Yeah, I
Yeah,
mean,
I mean,
in that
even
terms, Dubai is also good, where you can get some help. But if you want to go to any one of the these places, right, US, Australia, Canada, then you realize that there's a lot of things, right? If you want to wash your car, go put some coin, get a vacuum cleaner at the station, and then clean your car yourself.
Yeah. Yeah. We did that
I
once.
just did mine. I just did mine.
Um, I'm just very tired of cleaning the house and doing all of the chores. And
Yeah. Get
anyway,
Does
couple of
anyone have
iRobots and
the robot vacuum and it mops the floor too? I forgot what it's called. A robot kind
yeah,
of
yeah.
thing.
I will
iRobot.
have to. I think I'll have to get one. So, but there are lots of carpet that we have. The house owner had put, so it's painful to, you know, that thing will not climb on that carpet. It'll be very annoying. Okay. But anyway, we'll just see. Okay, perfect. So, with respect to data structures, so what we have, I mean, what we have learned in computing is something very, very useful. And this is something that most of the people who have not graduated from computer science miss. Okay, so we learned first the basic constructs. Okay, we learned recursion. We learned you know, bigger notation, right? And the complexity things. What else we learned? We learned what else we have learned so far? We learned the sorting, dictionary. What else? And binary search, and yeah.
Sorting, obviously.
Yes, sorting. So we learned the number system in the beginning. Then we learned the basic constructs like for loop, variables, and so on. Then recursion. Then we also learned about classes, right? And we also,
Yes. Yeah.
right, basics of linear regression, right?
Yep.
And yeah. All right. And that's it. Look like we are doing something meaningful with our life of weekend. Okay. Feel free to be very,
We did some Linux as well at the very beginning. So
yeah, we did the Linux also. Okay. And yeah, so I think we are doing pretty well when it comes to the, all right. Most important than me covering the topics, what I find very good about this particular class is that some of you who have never coded before, they were able to code and get things done. And like, for example, Neil was able to code and everything he's able to do. So this is something that I find this particular class to be successful. Maybe we are going a bit slow, but I think this is the correct pace. Okay. And yeah, we also solved really, really hard problems. Something that, like, for example, we build the recommendation engines flow. We talked about the challenges that we face. And I want to focus a lot more. I mean, this is like graduation and masters combined together in computer science and machine learning. And that's why I'm just trying to cut down on the junk part of the course. Like there are so many topics that people learn. I'm just removing those and focusing on what's important. And I'm very happy that most of you are able to relate with it and work with me on this. Okay. And yeah, because at the end of the day, it doesn't matter whether what all terminology you know. If you can't solve a problem, I have failed. Like my class did not go well. Okay, I would want everybody to be the problem solver. Okay.
okay.
And yeah, because all the time these days, what's happening is quite a few people reach out to me and say, "Hey, give me great candidates, give me great candidates," and I should be able to have that confidence on people in my class that they'll be able to solve the problems, and I should be able to connect everyone. So that is something that that's something that I'm hoping for, right? Like, for example, in all the projects that I'm running now, people keep on saying that give me more candidates, give me more people. And yeah, so I have connected a couple of my students who have finished the course in past and will be connecting more and as we go. Okay. So yeah. I mean, do these things not because you just have to complete the course or you just have to complete it. Do it because this is really useful for you. Initially, when new things are new, it will be annoying, but it might look annoying, but in a long run, you'll start enjoying it. Yeah. Okay.
Yep. Sandeep, one thing to ask actually. I mean, we talk about, data structures and whatnot, but we cover like some part, right? Like sorting and searching until now. But data structure is like a lot more what we read
Yeah.
in engineering,
Yeah.
greedy algorithms and your heaps, trees and whatnot. Should we start practicing it by ourselves or like the problem there is like I'm finding it hard, like whether I should limit my learning just what is going on in classes, or should I start picking up like any particular subject by myself and start checking in through. But then again, the problem becomes like the time, so kind of and this array actually like what to do at this point of time. This is one thing I always thought to check with you, but
Yeah. So see, there are only
or
very
otherwise,
few things that are left. Okay.
yeah.
Actually, most of these things you can derive by yourself. When you start solving problems, most of these things you can derive by yourself. There are few things which are not obvious, such as binary search or sorting and things. Okay, but my today's plan was actually talk about binary trees and trees. Okay.
Okay.
Yeah. Right. And I think trees, and one is there is just one is called breadth first search. Okay, and other is called the depth first. Okay, these
Yep.
are the two things that you just need to learn. Okay, that should be more than enough. Okay, all right, all right. So, okay, so let me first set a background, and this might look a very little awkward to you. Okay, so imagine that we want to, so when you study, let's say TensorFlow or any of these computation systems, there you will see a nice little thing called uh, TensorFlow. What it does is it takes a big graph, okay? It takes a big, just give me a moment, I'll just connect my iPad so that I can scribble while I talk. Okay, I'll just start with, okay. So,
Recording
sorry, okay. All right, so one of the coolest part about the say TensorFlow, okay. So what TensorFlow does is that it takes a graph of the computation. Okay, what does it mean by graph of the computation? Okay, in large term, when you see, oh, there is a graph, a computational graph, and it takes it and evaluates it, right? Now, let's say there is an expression saying 2 plus 3 into 4. Okay, how would you evaluate it? Okay, let's take a look. How would you evaluate it? Did anybody try it? Somebody gives you this in a text string, and then you have to evaluate it. Yes? Remember this
Yes.
discussion? Okay. So one of the technique was that you go from left, okay? You start from left. If it is a number, okay, put it in the stack, okay? And if you encounter an operator, you put it in another one. And you basically, when you get another number, you again put it here, okay? And then when you encounter a star, if, right, if this is, and you keep it here, if this star is, okay, let me give another example. So imagine that we have, let's say 2 into 4 plus 5, and we are starting here. So we basically, we will go from left to right. The moment, yeah, there is some sort of a noise that comes from time to time. Okay. So if we go from left to right, we'll see, okay, we encountered asterisk and then we encountered plus. So the moment we encountered plus, the previous thing we need to evaluate, correct? Previous thing we need to evaluate. Okay. So you basically basically put it in the stack and then evaluate the previous thing. Okay. Now, the another way to solve a hard problem is to solve a hard problem. Say, let me take another example, just be with me. Okay. So another way is take the expression and convert it into a data structure called tree. Okay, say for example, 2 into 4 plus 5. Okay, we convert it into a tree. Okay, we say that the parent node is plus, left hand side is asterisk, and this is 2, and this is 4. Okay, and this is 5. Make sense? So now we will talk about this, how to convert this expression into a tree a little later. Okay, but observe the beauty of it. Okay, observe the beauty of it. The beauty is that that once you have this side of things, right? Okay, once you have this side of things, we can basically evaluate easily. How would we evaluate? So this expression is converted into this tree. Is everybody okay? And can somebody help me with, let's say, 2 minus 5 into 6? How would you represent it as a tree? So
Into
will be the root.
and
okay,
then on the right node it goes 6.
right 6.
Left node
Left minus
5. And then 2 and 5, left and right. Yeah.
Right? And
Yeah.
basically, the way we are going to evaluate is first evaluate the left side, evaluate the right side, and then once you have this, evaluate the node. Okay, we can do it recursively, correct? Let's take a example of a bit more complex method. Let's say log of 10 to the power 6 plus 15, and the whole thing divided by 8. Okay, so how would we make the graph? So we'll say that first is division, the top one.
Yeah.
Okay, the right side is 8, and the left side is plus, and 15. Then we have on the left hand side, we have power, okay, and 6. Then we have log and 10. Make sense? So
Yes.
make it when we are solving this tree, we can solve this tree very quickly, correct? We will say start from here, okay, and compute the left, compute the right, and then compute the division, right? Now, how to compute the left? How would you compute the left? This one, compute the left, compute the right, then add the two. How would you compute the value of this? Compute the left, compute the right, and to do the power, and so on. So one system can send an expression like a tree to another system, and then the another system can do the evaluation, right? We can also do all sorts of magic on top of it, that one processor is processing this left side and another processor is processing the right side, and we basically divide and conquer. Okay, one computer can have multiple processors, right? And if the computation is too much, we can divide the work into one processor and second processor and get it done. Make sense to all of you? No? Okay, now
Repeat this again, Sandeep.
so basically
The
when
processor side.
yeah, so imagine that you are having multiple processors, right? When we say GPU and all of that, what actually it is. And why we need TensorFlow to do the GPU? Because entire calculation is a big graph. There's a noise that is coming. So the entire when you say you're training a model is nothing but lots of mathematical operations or computational steps. Okay, it's a big graph of calculation. You can say big tree of calculation. Cool. You
Yep.
start at the top. Okay. And you want to, let's say you have multiple processors with you. So what will you do? You'll say, okay, do this calculation on one processor and do this calculation on another processor. And that's how you will get the work. Okay. Now, make sense?
Yes. Yep. Yeah. Yep.
Okay. Now, essentially, the thing is that converting a text string to a tree is not a trivial operation. You have to use recursion and you have to do all of that. But once you have converted into a tree, then you can do a lot of magic. Okay. So a very important part is to represent expression calculation into a form of a tree. Okay. Similarly, internally, when you think of a SQL query gets converted into a tree. Okay. When you have like a SQL query, you send the SQL query to the server, it creates the tree, and it basically does the editing. Okay. Like for example, the product that I've built is called Turno. It takes the SQL query, creates a tree kind of thing, and then it picks and chooses and edits it. So once you frame a tree out of something, then you can do a lot of magic around it. For example, I'll give you something that I did during my college. During my college, I participated. I'll be very honest with you. During my college, I participated in a contest called Do the Differentiation, right? You remember those formulas? If it's x square, the differentiation is 2x, right? If it is x cube, it will be 3x square. If it is x sine of x, it will be cos of x, correct? Right? So basically, I participated in this contest where my code will take x square and will print 2x. Okay? A user can enter anything. If somebody enters sine cube, my system will say 3 of sine square x cos x. Okay? So here there is a lot of symbolic manipulation, you see. Now, how to do it, I did not know. Okay, I just jumped into it and I basically said, okay, I'm participating, and I had no clue how to solve it. Okay, and that's when I ended up going back and forth through hundreds of books, and not hundreds of books, through like 5-6 books, going through them over and over and trying to figure out how would you solve such kind of thing. Okay, so this is where I actually learned most of the data structure like, by the way of trying to solve only one problem, this one. Okay. And this is when I discovered that, oh, there is something called a tree. If I can convert this thing into a tree, then I can edit the tree. Okay. So if I say, okay, let's say, if I have, let's say, x square plus 2x as the expression, it would look like plus and then square, okay, square and x, or you can say power and 2, and this is multiplication, and then this is x, 2 and x, okay. So once I created a tree, I could basically transform the tree into differentiation. All I did was, if it is addition, take the left-hand side, okay, differentiate it, take the right-hand side, differentiate it, and put them together. That's all. If it is power, then what you do is, if it is power, what you do is, whatever is the power, the next term will look like this, okay? sorry, power, if it is power x square, for example, so what do? Power of something, okay, whatever is the expression, what do? You say, okay, I'm going to say multiply 2, okay, and then I'm going to say power, and whatever is the expression here, that, and 2 minus 1. Okay, so like that, basically, if you have a tree, then you can edit the things easily. Okay, so the most important thing I'm trying to emphasize, the utility of a tree in here. Okay, so if you have a tree, then you can solve it. Similarly, when you think of a browser, like this, okay, let me take, is there a good simple example? Let's say, okay, so this is probably the simplest website you will find. Okay, so if you think of this thing that here, okay, this is all right, from where to where? Yeah. So if you think about this, right, this page is nothing but a tree of elements. Okay, it has, right, it has the, right, it has the top element called HTML. This is first child, second child, third child, and they have another children. Okay, so, and like that, it keeps going. Okay, and so the web page is nothing but a tree of rectangles. It is a tree of rectangles. Okay, tree of rectangles, and you basically, when you print them, I mean, when you render them, what you do? Render left, render next element, render this, and you keep on going bottom. So if you think about it, that this, the way browser works is it takes HTML from you, creates a tree out of that HTML, and then uses that tree to represent rectangles or draw rectangles in the on the screen. Correct? One of my favorite questions for very senior engineers is like, how would you design a browser? Okay, and when they go for that, I look at, are they able to think in terms of large complex designs? Okay, and I actually ended up in one of my career jobs, I ended up designing a text editor. Okay, can you believe a text editor? Like just like HTML thing. That was probably the hardest thing I had done. Okay, and yeah, now that time I realized that the entire thing is a big tree of elements, and we have to render them and do the drawing. You know, when you hear the word text box, the way I see the text box is, it's a rectangle, two rectangles drawn from left to right, filled with some color, and then there is a focus. When you put a cursor in that, you have to blink it, and when somebody types it, and you have to enter that. Okay, but the most important part was to come up with a tree structure so that we can render it. Okay, now trees are very useful. Okay, so imagine, for time being, let's assume that we have an expression tree. Okay, let's try to create a simple expression tree. Okay, we would like to create an expression tree for 2 into 3, okay, plus 4. Okay, now if you see, a tree is a recursive data structure. Okay, what does it mean by tree? Contains trees as children, those children contains other trees as children. So what we need is a node, not the tree. Okay, so you can say class node. Okay, and then we can say def init. Okay, and we can also say self, and what was that, type. Okay, type, we'll just say 0 or 1, okay, by default 0, okay, and then there is a value, okay, right. I'll just put it here, note that type 0 means it's an operator, okay, and yeah, it's an operator. Otherwise, it is a value. Or do you want to suggest something else? Okay. Okay. All right. Now, so each node in the tree that we just created is going to be either an operator, like remember this diagram very clearly. So we will create a tree. First, we will have plus 4, asterisk 2, and 3. This is a node. This is a node. This is a node, and so on. So every node has either an operator or a value, okay, and basically every node has got a type called operator or the value, and every node has got the actual value. Okay, now in case the okay, now in case okay, so every node is either a operator or operand, okay, and every node has got left and right node place. Okay, so it's kind of a recursive data structure. Okay, just like we have recursive function calling itself. Here there will be the data structure calling itself, defining the value itself. Okay. Okay. So, all right. So I just defined these left, right, type, and I'll just remove E. I'm feeling very uncomfortable with, because it might be conflicting with that. Perfect. So that's it. That's my node. Okay. Now let's take a look at it. How does it look? We have node. Okay. And we are saying first, first we'll define the bottom node. Okay. Let's call it 2 is equal to node. Okay. I'm putting the type to be 1. 1 means it's a value. Okay. And the value is 2. Okay. Then 3. In the same way, I define 2 nodes. Okay. Then asterisk, right? Okay. This is the next node. Now, okay. And I can also write something like left equals none and right equals none. Okay. So I'm just going to put this into left and right. That's it. Now I can say here I'm defining the type at 0 and value as asterisk. Perfect. Now, then I'm saying add that at the top. Okay. Yeah. One more thing we forgot. Here, the left node is 2, the one that we just defined, _2, and right node is _3. Okay. We can also say explicitly left equals this and right equals this. Notice that to avoid, because a variable cannot have the name like 2, so I put underscore before it, so it becomes very easy to see. Okay, so now you see this multiplication node, okay, contains left and right. Okay, now what I'm trying to do is I'm saying add, and let's just define the _4 also. 4 equals node, and say type equals 1 and value equals 4. Okay, and now I'm saying let's just call it tree, the final one at the top, node, and type is equal to the type is equal to 0, which is addition, value equals a string plus, and left equals to multiplication, MUL, and right is equal to _4. Okay, let's see. It says init got an extra argument. Okay, got an unexpected thing called type. Okay, perfect. Now that's our tree. This is our tree. Okay, this tree has got, you can see, well, okay. All right, let's define a method called print tree. Okay, print tree, so that we can see what's going inside it. Okay, print tree, and we say self. All right. Now, how would you print this tree? How would you like to print this tree? Okay. All right. Or let me say that we'll call it a string method. Okay. We'll call it a string method. What it does is it returns the value in the form of tree. Okay. We'll say operator self dot type. Okay, self dot type. All right, I'm just going to convert this into a string. It's 1 or 2, and then I'm saying the value is going to be, or can I just use those clever things? I will say there was a F thing, right? Format. So we'll say this self dot type. Okay, self dot type. I'm just trying to print it. Okay, I'm just trying to print it and saying self dot value, and I'm saying here, okay, how would it look good? I'm just trying to, okay, I'll just say it this way. Okay, and all right, left equals, okay, left equals to self dot, okay, let me do the recursive thing. I'll call the string method on left and right. Okay, self dot left dot string. I just called it. Okay, I'm calling the same method on left hand side and on right hand side. Okay, so all right, or we can say left comma right string. Just to, I'm taking care of the null cases. Okay, if these are both do not exist. Okay, so I'm saying if self dot left, then do this. If self dot right, then do this. Okay, and I can just say here left string and right string. Good. All
Right
right.
string should be in the curly braces.
Yes, thank you. Good, good. I am happy that you guys are paying attention. Okay, so what I'm trying to do is I'm trying to just put this.
But Sandeep, left string and right string equation are same because here the thing self dot left, self
Thank
dot.
you. Thank you. I'm happy that, yes, you are still awake. Okay, everybody is awake. All right, very good, very good. Let's see what happens. Would it work? Okay, we'll just say tree dot string. Okay, it did something. It doesn't, I don't like this format. Would you recommend something? Should I put a new line here? Okay. Oh, I did not put a curly bracket here. Okay, so at the top, it says the type is 0. Okay, let's remove this type. Its type is not really making it ugly. Okay, so plus, then inside that, there is asterisk. Okay, then inside that, we have this. Okay, so what if I could just, how to print a new line? Anybody? Can I print a new line? If I could just bring.
You're allowed to give escape character, right? Because you're in code, so you're allowed to give the escape character.
It won't, okay. And all right, I'll just also try this.
Good.
It won't work.
No, you'll have to give an escape character.
Okay.
Double.
I think this is okay. Is it okay to you? No. I'll just put one bracket here. Yeah. So we have plus at the top. You can see the tree when we were printing. So we have plus at the top. Then bracket is started. That means there is asterisk. Then for asterisk, there is 2. Okay. And there is 2 doesn't have anything on the left or right. Okay. And that's why it's blank. And then the next element in these brackets is 3. Okay. And 3, this is blank, so it's not going to do anything. And then that's about it. And then we have we basically, in here, we can see that this bracket closed and we have 4. So it has internally, it has created a tree. Okay. All right. So we were able to successfully create the tree. Got it? When you think about displaying a beautiful folder structure on the left side of the file system, this is what is going on inside. We load the data from the system, like the hard disk, into a tree and display it. Everybody okay so far?
Sandeep, could you just explain the output again? Like that process a bit more like on detail?
So I said value, then arrow, then one square bracket and another square bracket. Correct? So plus is the value, the left side string and right side string. For this plus, this bracket starts here till here. Correct? Right? And I can also put a comma here just to be very clean. Yeah. So for this plus, this entire thing from here till here is the children, right? First child is where, not good idea. Not good idea. I'll just put these two so that we can, I'm just trying to figure out how to display it nicely. Okay. How to display it nicely? That's what I'm thinking. All right. Okay. Okay, I'm going to use this technique, like we will keep on increasing the indentation. Okay. So we will pass the indentation in the beginning. Okay. So while displaying this value, right, we will say value equals indentation plus self.value. Or just put that thing. I'll just put this indentation here, like this. Okay, so that it'll look a little nicer. Okay, and I will say the left side of this, okay, indent plus, okay, indent, I'll say new line, and it should be okay. Will this be okay? Or do we need to do something else? Okay. And while calling these, I will just say indent plus 1, 2, 3, 4. Okay, I'm just increasing the indent by 4. Okay, it did not how to make it. Oh man, how would you make it? Subodh, you were saying something. Help me out. Okay,
Yeah,
how to
I was.
this?
Yeah, what I was saying is, you the new line character, right? Put a this thing escape character, so it will actually come as new line character.
Like this?
The double one, yes.
Nah, it's already escaped. Okay. No. Just can somebody look up? This I did not know that this will do this kind of nonsense with me. Okay. All right, let me see if I can. I will say indent here, and I'll put %s. Okay. %s. I'm using the older technique to represent it nicely.
Curly braces.
Oh man. Why it's just discarding whatever I'm doing over here? Like, why should it not just okay? At least some new line came, or is it not the new line?
No, it's not the new line.
Sandeep, could you just test one thing while I just read? If you put inside a curly bracket, if you put CHR 10, which represents
Okay.
the slash new line. Apparently,
Okay.
it works as a new line. Maybe.
No.
Oh, that was the different thing. If you put the F here, then it'll work. Okay. Yeah, does it work?
Mhm.
All right. Wait. This can't be.
It is a string, so I think it is not changing it to the printable format. So if you
Yeah.
if you create a print method, it should work.
Okay. I think this would do. Sorry. Okay. All right. So. All right. We don't need indent here. We just need. Okay. Now you can see clearly. All right. 1, 2, 3, 4. 1, 2, 3, 4. Okay, now it looks good. And I think we can just put the indent here as well. Yeah. I'll just do indent here. Yeah, now it looks good. You see? So this is the parent, first child, a second child. First child's children are 2 and 3, and 4 and right. Okay, this looks better. Okay, so if you do the print, that'll do that. Thank you, everyone. Okay. Yeah, I just start relying too much on Jupyter and forget that there is something called print statement, because this string was returning that. Okay, and I want to see if right. So there is a method called right, toString method in Python class. Okay, so that method is returns a human readable or informal string representation, and or we can use something called REPR. Okay, so if we change the name of this one to REPR, okay, and that should also do the magic. Okay, so you could just say print tree, and that should be. Okay, so when you say tree, it'll look nicer now. Okay, by default, internally, when we are typing an object's name, its REPR method is being called. Okay, so yeah, we created a nice method to represent our object. Everybody okay so far? I'll just make it 4. 4 would look better. All right, or just put a tab. Okay, yeah, this is way better. All right, so every time it's adding to tab, I think just adding too much of tab. Okay, and why it's doing so much of tabbing? Yeah, this is good. All right, so we were able to create a class called tree, and we recursively printed it. Do you see this recursion here? So we are calling REPR method on left and REPR method on right, and we are doing it recursively. Okay, and the moment we hit left is none and right is none. Okay.
Will it still work if we don't use type keyword? Because I think we are not using it.
Which one? Yeah. So we are keeping that internal. We can just, here we can just put one colon and then say, okay, I want to display the type as well. Okay. All right. So we've just said it's plus and the type is 0. It's asterisk, type is 0. It's 2, the type is 1. 3, the type is 1. 4, type is 1. Okay. Got it, everyone? Now, who can help me write a method called eval? Okay, we are writing a method called eval. It takes self-object. Okay, how would you evaluate this tree? Okay, anyone wants to explain to me the logic? So we have a tree representing a expression, and we want to evaluate this expression. Yes?
Eval left, eval right.
Okay. Evaluate. Okay, so if self.left, okay.
Yes.
Okay. One thing we have to do, make sure that the if type is what? If type equals to 0, return, what value should we return? If it is 0, sorry, type is 1, that means we just have to return value. That's the value of the node, correct?
Yes.
Otherwise, if type is 0, that means it's an operator, correct? All right. Now, here we'll say if left, then, okay, I'll say self.left. Self.left. If self.left is there, what do? We evaluate left. We'll say eval
Self.left.
Eval, no, we'll say self.left. Yes, dot eval. Okay. So if that it's an operator like this one, the plus one, we will ask it to evaluate left and then evaluate right. Okay. And we will just call both of them L and R to be none and none. Okay. We'll say if left, if self.right, if it has right node, we'll say right equals to self.right dot eval. Yeah. So we calculated R and L.
Yes.
Okay. If L, okay, if left and right both are none, if L is none and right, okay, or R is none, okay, which means that it doesn't have an operator, okay, operand, though it's multiplication or things like that, we will throw an error, okay? We will, if there is a asterisk and there is nothing on the left hand side and there is something on the right hand side, then basically there is a trouble. Okay, there is a trouble. Or let's leave it here. Okay, let's leave it here. Okay, now we start implement. So we evaluated left, we evaluated right. Okay, and now we got the value from the left, we value got the from the right. Now we start implementing things like this. Okay, if what is that, value equals asterisk, okay, return left into right, okay, else if value equals plus, return left plus right, else if value equals minus, return left minus right, else if I know that this looks very ugly, but we'll come back to that. Okay. And division will return left divided by right. If value equals, are we forgetting anything? Let's just say power. Return L. And that's it. Okay. For now, we just implemented this thing. Okay. What we forgot something? All right. Let's see. Okay, so this is my tree. We created the tree. This is how it looks like. Now we are saying tree.eval. Okay, it says type is not defined. Where the type is not defined, we are okay. All right, type is not defined. Where did we look at this type? Correct. So we'll say type equals to self.type. And we'll say value equals self.value so that we don't have to type too much. Okay. So the answer seems to be 10. Does it make sense? 2 into 3 is 6 plus 4 is 10. Okay. Everybody okay with this? This is the logic we wrote. We said if it is a value, return the value. Otherwise, what you do, check. If it is asterisk, then otherwise compute left, compute right, and then just apply those operators. Correct? So we are calling eval recursively. You see the recursion? So tree makes it possible to do the recursion. Everyone okay?
Yes,
Yeah.
Andy.
Okay. Now, I know that the tree is notorious amongst people because apparently most of the people believe that tree is of no use to computing in practical computing, right? You must have seen those interview memes where they're making fun of an interviewer because in interview the person is asking some random tree question which has no relevance in physical life. But as a matter of fact, tree is way more relevant in physical life. Okay. Is it okay, or is it going too much over the head? Feel free to, give me feedback. So we just created.
Going into head, but I think we need practice.
Okay. Okay. Anybody else?
It's been a while means the concepts are all fine, but obviously, we need to practice, or at least I need to practice more. I haven't been doing it, and
Right.
it's been a while since we have coded, or at least I have coded things.
Okay. Okay.
Is
think
it possible?
yeah.
Is it possible if we give input as a string and it converts directly into tree? Because now we are using object one by one to creating a tree.
Yeah. So you are saying that can we define a method called toTree? Okay. And it takes expression as a string and it returns a node. Correct?
Yes.
All right. All right. Who can help me with this? This is the hardest part of it. Okay. So if I call toTree with 2 plus 3 into 6, right? to the power 2, it should be able to do it. Okay, will you be able to build it? Yes. This is the upper end of computing. Okay. And yes, if anybody is up for challenge, you should give it a shot. Try this, and let me share. What was the name? I just keep coding these things. These are pretty neat things to code. All right. I had more repositories. Let me see. I was writing one optimizer. Oh man. I've done so many random stuff. Okay, never mind. So I will take it from here. Where did I publish my calcul chart? Somewhere I had published it. Yeah, here. Okay, so I want you to take a look at this code that I wrote. Okay, so what it does is it takes an expression, okay? It takes an expression and it calls the left and the right, okay? And essentially, this logic should give you, if you read through it, you should be able to build it, okay? I can do it, probably it'll take me probably 2 hours of time, but I should be able to do it, okay? So what you need to do is just take a look at this code, okay? And instead of evaluating the expression, so you basically have to do the code, okay? And those who are really interested in learning this art of this technique is called parsing, okay? So we are parsing an expression string into a tree, or we also call it token tree, parse tree, okay, and so on. Okay, this is a common thing to do. Okay, like for example, people take SQL, parse it, and create a tree. And once you have the tree, then you can start optimizing the tree, evaluating the tree, doing the joins actual work. Okay, exactly the way we did here. Okay, so the first phase called parsing is something that I would want you to take a look at my code and you will get an idea on how to create a parse tree. Okay, so instead of evaluating values, start returning the node. Okay, and that's about it. So that's something that you should and can do there. And if I get some time, I can code it up. Okay, it's this way that you basically recursively call the add and subtract. Okay, it keeps on consuming it, and the moment it hits the smallest value, it consumes it and return the expression. And then this one starts the job and it'll keep on returning the tree. So recursively, it'll build the tree. Okay, so the same thing is true for everything in computing. You have C++, you parse it, and then you create a tree. Okay, and then you execute it. Okay, now this whole thing is so common that there are tools called compiler. The name compiler comes twice, okay, in the name. All right, so there is tools called yet another compiler, YAC, okay, which is what it has been used to design C++, C, and Java. Then Java came with their own compiler, Java CC. Then the one that industry uses is called Antler. And Python as a language is converted into tree using Antler. Okay, so every language has got a grammar, and you represent the grammar saying the addition is more than this and so on. And then once you have that, you basically create the code automatically. Okay, so this whole work has become so common. It has become so common that what people have come up with these marvelous tools which let you define the grammar, and then this tool will parse it and create an expression for you, the expression tree for you. Cool, right? So those who are interested, they can try the Antler. Okay. Python has been coded like that, right? So I would say that give it a shot, those who are interested. And I have already coded this simple expression. Take a look at it. It is a fair amount of cryptic code. It's a recursion, a lot of recursion. If you see my code, okay, and if you see my code here, what it does is, okay, the entry point of this code is very, very mysterious. Okay, is very mysterious. So when you give it an expression to evaluate, what it does, it basically sets all these values, and then first thing it does is it calls add or subtraction, addition or subtraction. Okay, when you enter this method, this actually calls multiply or divide. Okay, and then it keeps calling multiply divide. So it's assuming that your expression is made up of something plus something. Okay, so first it calls add multiply divide or something, and then another again multiply divide, and then whatever is the value from the left and the right, it basically adds them. Okay, you can see here, first it calls multiply divide, so subtraction calls multiply divide. Okay, and then it again calls multiply divide, and then once you get the result, you basically, and it also checks whether it's a plus or minus. Okay, it checks plus or minus. If it is plus, it adds, it keeps on adding, right? So it is thinking that This is A, B, and then again C. So it keeps on evaluating these values and so on. So it's saying that addition is made up of multiplication, multiplication plus minus add subtraction expression is made up of multiplication plus minus multiplication plus minus multiplication, like that. Okay, and then multiplication is made up of power and multiplication power, like that. So if you see, multiply divide method is going to first consume this way. So essentially, it's a very interesting thing. Okay, so this multiply divide is calling the expression here. Okay, this expression is checking, calling atom. Okay, and so on. So most highest priority value is atom. If it is 2, then you don't have to check anything. That's it. Okay, and that's about it. And so that's what is happening here. EXP means exponent, not expression. EXP means power. Okay, so power is the last and most important thing, and so on. So this pattern of computation is so common that you know, people have created a grammar for it. Okay, so you essentially define a grammar like this. Okay, where did it go? Yeah, you define a grammar like this, saying my expression is made up of other expression, multiplication, division, other expression, and then expression is made up of expression and add, subtract, other expression, and expression could be made up of a number. Expression could be made up of bracket followed by expression. Okay, so this is right, and then here the right int is nothing but 0 to 9 and so on. So you basically define it like that. All right, so those who are interested, walk through this code, and those who can understand this code, we can discuss it next time. I can guarantee that you'll have lots of doubts when you look at that code. Okay, I invite you to read through this code and think through it. Okay, it took me a while to figure it out. It took me a long while to figure it out how it's working. So I want you guys to read through the code and try to figure it out. Okay, I want you guys, it's just simple plain recursion. All right, so
Sandeep, I actually had a general question. See, for me, like, I think the challenge which I'm facing right now is how exactly to use recursion within the code. Like, let's say for sorting, like, what is the correct code to put in so that it activates, let's say, the recursion. So even for quick sort, actually, it's, I think, thanks to Veena, I was able to figure out, let's say, the recursion part. Rest everything, I was able to do it myself. So I think that's what I wanted to know. Like, how can you practice, let's say, recursion so that you know, okay, this is the right thing to do at the right point in time?
solve more problems. Okay,
Easy.
solve more problems. There's only one thing. Okay, there's only one thing, and yeah, right. So solve more problems. Create a discipline to solve more problems. Okay, that's the only thing, and that's the only thing. There's no other thing. Okay, and that's the only thing. Okay, and you might think that I'm able to code quickly and I'm able to do everything, but reality is that I've done all of this quite many times. So for me, these things are just natural. Okay, but
So,
I'll tell you very honestly, when I looked at this particular code, right, for the first time, this code, okay, I read through this code somewhere on some website, okay, and it took me a long while to figure it out. Okay, so when I was creating the differentiator, what I did was I took this kind of a code from somewhere, modify this. Instead of creating, result plus result, I started creating the tree and return the node. Got it? So I basically created a tree and return the node. Okay. So is there a good recursive parser of expression in Python? Somebody must have written the same thing what I did. Okay. So expression is term plus expression, term minus expression, or the term itself. Okay. And yeah. Yeah, parse expression, token plus token, parse term. Okay. Will it work? Yeah, so I think you can try going through this kind of code. Okay, so read more code, do more code, and that's how it will be. So you can take this code and try converting it into Python, and then or just search for some other code and try understanding it. And instead of evaluating the value, convert it into tree. Okay, how would you convert it into tree? Let's say here we are saying result plus equal to the result. So instead of adding the left hand side and right hand side, the result is going to be a node. What you do is you put the plus at the node, and left child is this, right child is this. That's all. Okay, and that's about it. Yeah, you were saying, Subodh?
Yeah, I was saying that from what I understood, Neil's question was that how to identify which part to recurse in a given logic, and then how to identify and do it, right? What we were taught like 20 years back is like try to solve the same problem on paper. Like for example, if you want to do tic-tac-toe, or if you want to do say Sudoku, right? You will try to solve the same problem, evaluate and write those, try to solve it by hand. Then you'll understand what part you're doing again and again, right?
Yeah,
That part will go into recursion. The only thing you have to keep in mind that if you put anything in recursion, you should have a way to get out of it. There should always be an end condition, right?
correct.
So if you identify that, then you will be able to identify anything, right? So for example, if you want to do parsing of this, right? What you're going to do is you're going to see two numbers and then figure out, okay, I'm going to solve this, and then I'm going to solve this the solution of that with something else and so on. So that means that you are going to do a recursion on it. The exit will be, it will give a return value,
Yeah,
right?
yeah,
Same thing with you know what we did in recursion, the merge, no, the merge sort, right? There
yeah.
you split it, and then you split it again, and then you split it again. So the splitting and then taking that value and splitting, that goes into recursion, so on.
Right, right, right. Perfect, perfect. So I think, yes, that is the common theme, but internalizing it, right? When you are able to explain it to somebody, that means you have internalized recursion 50%. If you are able to solve more problems, you have internalized it like 100%. Okay. So one of the, right, good codes to solve is, like, for example, okay, parking lot puzzle. Okay. Parking jam, parking. Okay. What do you call that? There is a, yes. Okay. So here is a simple puzzle. Okay. And this is your car. What you have to do is you have to, this is called, car park puzzle. There is a name for it. Yeah. Can you open it? So yeah, so like this puzzle that you see here, okay, and okay, so basically, you have to, let's say, solve this puzzle. How would you solve it? Okay, so you will start at some point, try all possible options, and then you basically do the next. Okay, so essentially it is, and then you go back to the previous step and so on. So there also you will you try solving this using recursion and you'll get a fair bit of idea. Okay, so yeah, all right, that is yeah, it's called car park puzzle, or this is a better name for it. Okay, there is a better name for it. Once I know the name, I'll ping you guys. Okay, now, so simple answer is practice more, and that's it. Okay, and as Subodh explained, you have to basically think in terms of can I do it for n-1? Okay, can I reduce the problem to n-1, and then you use it. Okay, but it's easier to say than actually do it. Okay, and that's where most of the energy goes into. All right. Oh, actually, my keyboard right now on the Mac shows all these icons. I never knew this. Oh, nice. Not bad. Not bad. All right, let's move on, everyone. Yeah, that's nice. Okay, let's move on. Perfect. So what we learned was that using the data structure, we were able to solve this kind of problem, right? Now, so this is called the binary tree. Using binary tree, we were able to solve these kind of problem. Okay. Now, there is something called a binary search tree. Okay. And the way binary search tree works is that it keeps something at the top. Okay. Binary search tree. Okay. So the way binary search tree works is, I'll just show you animation, okay, if that makes sense to you, and then we can talk about it. Okay, so what is a binary search tree? Binary search tree stores data in the form of tree, and it basically it essentially it quickly searches the data in this tree. Okay. In case of binary search, the data has to be sorted in a increasing order or decreasing order, right? But if your data is continuously changing, what will you do? Let's say you have a database and the data is coming in from time to time. What would you do? When you have record and people are inserting into the record. So would you keep on sorting the data all the time? Let's say you have the data which you sorted, and new data is coming all the time, right? You will have to keep on sorting the whole data again and again if you want to support the search, correct? So instead of doing that, people have come up with something called a binary search tree. Okay, so let's say we have you know, okay, we created, we first added the data 10, then 20. So you notice that when we added 10, it just added a node. And when we added 20, it added node to the right of 10. Okay. If I add 5, it will add it to the left of 10. You see? So to the left, it is adding smaller number. To the right, it's adding bigger number. Now let's say I add the equal number. So it will go to the right. So for every node, all the values on the right are either equal or bigger than this node. Okay. All the values on the left are smaller than this node. Okay, you can see the value on the left of 10 is 5, value on the right 10 is 20 and 10, correct? Value on the left of 20 is 10 and so on. Okay. Now, it's a simple structure. Okay. It's a simple structure where we are keeping values bigger than a particular value or equal to that particular value on the right-hand side and the smaller values to the left-hand side. Okay. Now, let's say I have 25. Where will this go? 20, when I say 25, it'll come here, check. If the 25 is bigger than 10, yes, then it goes here. It says, okay, is the 20 bigger than 10? Sorry, is the 25 bigger than 20? Yes, so it'll come here. Okay.
What happens if 10 again comes?
10 again comes, let's see. So it would come here, check. Should the new 10 goes to the left or right? It will go to the right because on the right hand side, equal or big values we are keeping. And then it'll come here and check, should the 10 go to the right or left? It'll go to the left. Then it'll check, should the 10 go to the left or right? It'll go here. Okay, let's see.
Something, is it not changing its center?
Yes, good question. No. Okay. Now, because of this, what happens is the tree is becoming unbalanced. So there are techniques to make it balanced. Okay. So this is called binary search tree, and binary search tree is very often used in the situations like database, where new values are being added, and like a variant of binary search tree is used in database indexes when you are adding a record, deleting a record. Okay. And let's say I'm adding 1. Okay. And then 2. Okay. Are you guys okay? What's happening in the binary search tree?
Yes.
Yeah.
Okay. So now my question to all of you is, if you have to create a binary search tree, what will you do? Can you do that? Everyone? You want to create a data structure which allows you to insert a new element and delete an element and find an element. For example, I want to first find, let's say 2. Is the 2 existing in this? So first it'll go here. Is the 2 less than this value, equal to this value, or greater than this value? If it is equal to this, less than this value, it'll go here. It'll ask 5, can you tell me 2? It will ask 1, can you tell me 2? It'll ask here. Okay. So how many hop? 1, 2, 3. So the total number of hops are going to be equal to the height of the tree, which is log. Log of the total values is the height of the tree, right? And therefore, lookup is log n, insertion is also log n. Okay, so let's take a look at again. All right, so it's searching for, so it basically, right, let's say we are saying search for 0, goes left, and says not found. Okay, but if I say search for 10, okay, it will go and quickly return true. Search for, let's say, 25. Okay, good. Is everybody okay?
So Sandeep, when you delete 10, does it delete all 10s or like the first 10 friends?
Good question. Let's see. It should delete all of them, or one. I think it should delete one. Yeah. Notice the delete, everyone. So what it did was, when it was deleting, it replaced itself from the left-hand side. Okay. And if the left-hand side was not existing, then it would basically make the right-hand side at the top. Okay. Like, for example, if I want to delete 2, what will happen? If I want to delete 2, let's say delete 2. Okay. So 3 became the parent. Okay. If I want to delete the next 10, what will it do? Okay. Let's see. Delete 10. Goes here. Delete. See? So the strategy is simple. Okay. So now, can you guys help me code a binary search tree? Okay. Let's say I'm defining BST. Okay. And I'm again just going to go with this sort of the. Is everybody okay so far, or does it look too complex? Yeah, give me some signal. Visually, you are able to see like advantages of binary search tree.
Yep.
Right? So if you basically just keep these values in a list, okay? So here is the problem statement, right? The problem statement that we are trying to create is that, okay, right? When to use binary search tree, right? Problem statement is we have a lot of additions, okay? Deletions and find operations on our data continuously. Okay, we need a good mechanism to do it. Okay, now you might say that, okay, why not? Right, all right. First suggestion will be, why not list? Okay, why not list? Okay, why not list? Because adding an element or inserting an element takes what's the order of inserting an element if you have a list? Okay,
Order of 1.
right, order of 1. Okay, it's an unordered list, right? So I'll just say insert takes order of 1. We'll just add it to the end. Okay, and deletion will require searching that element and deleting it. So delete will take how much time? Order of n. Okay, deletion will involve find, which is order of n, and then remove and move all the elements after that element up. Okay, right? Okay, moving elements will take again order of n. Now finding elements will again take how much?
Order of n.
Order of n. Okay, which means that this is going to be very inefficient. Okay, Can we do better? So if you do better, right, why not sort the data? Let's say we have a sorted list. Why not sort the list? Okay. And all right, this looks super ugly. And yeah, why not sort our data? Okay. Why not sort the list as and when? Why not maintain a sorted list? Okay. Now, if you maintain a sorted list, then as and when the inserts are happening, you'll have to sort it. It will be n log n. Okay. The order will be n log n, and find will be log n, and then delete will also be order of n. Because when you when you delete an element, you have to move all the elements back to beginning. Okay. Now, why not do it in a dictionary? Okay. So in case of dictionary, insert will be order of 1. Okay. Delete will be order of 1. Order of 1. And find will be order of 1. Okay. Correct. So from all the aspect, dictionary is great. Okay. The only challenge is that dictionary is inefficient when it comes to the memory. Okay. It becomes too clumsy because internally it's just taking too much of memory. Okay. So too much. Okay. All right. So this is where the binary search tree comes into play. Is everybody okay? Is there any other option would you suggest? All right. Are you guys okay so far with whatever we have discussed? No?
Yes, Sandeep.
So if you have like binary search tree, you can basically, let me just define binary search tree like this. Okay. We'll just define something called node. Okay. We'll say this is my node. It has got a value, it has got left, and it has got right. Okay. We'll just say self.value equals val, and then self.left equals left, self.right equals right. Okay, that's it. And that's our node. Okay, now let's define a class called binary search tree. Class called, right, BST. Okay, now we are basically doing it to keep a track of, okay, and we'll keep a track of the root node. Okay, root node, we are going to keep it a separate one. Okay, we'll just say self.root, and we will keep the value of this root node to be, the value to be, let's say, -1. Just to, this will be a dummy node. Okay, all the children that will be coming to the bottom of this node. Okay, or let's just keep this as none for now. Okay. All right. Or should I do that? Yeah, let's just keep this way. Okay, now, so right now the binary search tree class is having the root node as none. There is nothing there. Okay, and yeah, now we are defining a class called insert. Okay, self, and we are saying, yeah, we are inserting a value. Okay, so what are we going to do? When we are inserting a value, first thing we'll do is we will create the node. Okay, so this is my node n equal to node, and the value is going to be this value, and that's it. Cool. So I just created the value, the node. Okay, this is the node to be inserted. All right. Now, what's the logic that we're going to follow? We're going to say, okay, we're going to say this, that, right, or should we can also just define a method called insert in this. Okay, and we'll say node, right? So when we are inserting a node, what do we do? Can somebody explain me in the logic? If you see here, where was that? Yeah, when we insert a node, what's going on? Let's say 8, right? You will go to the top, check if 8 is bigger than this or lesser than this, and that's it. Okay, so we can just define a method called insert at this level. Okay, let's say here we are inserting this node, so we can see if self dot value is, or we can say node dot value is less than self dot value. That means it'll have to be inserted to the left hand side. Okay. All right. So if self dot left, okay, equals none, okay, then we are saying self dot left equal to node. Okay. Otherwise, repeat the process. Make sense?
That insert method should go in binary search tree, right?
No, I'm just calling on the node itself. Okay. We'll see if we can just get everything done through this node instead of doing the recursion. Okay. All right. So I'm saying that here is my node. Check if its value is smaller than my value. If it is smaller, then it goes to the left. And if the left is none, right? Then I'm just assigning this node to left. Otherwise, I'm calling it recursively. Correct? Else, if self dot right equals none, self dot right equals node, else self dot right dot insert node. Okay, makes sense? No? Yes. And I can copy my code of this thing, REPR. Okay, let's see how ugly does it look. Okay. Right. So left is string, right is string, this is left and right, and okay, and I'll just say value, we don't need type. Okay. Okay. So this is how it looks like. Okay. So Okay, so what we are going to do is, all right, and yeah, we created the node. If self.root equals none, then self.root becomes n, else self.root.insert. Okay, so let's see. This is my BST. This is my BST. Okay, and I'm saying BST dot insert. I'm adding 10. Okay, then let's check how does the root looks like. Okay, root looks like this. Okay, and then I'm saying 12. Then let's see how does the root looks like. So at the top there is 10 and then there is 12. Okay, I will just try to see if I can print left, okay, and right. I'll just print left and right. Okay. Okay. So we have inserted 10 to the right. Make sense? I don't know why it's doing this. Left and right. Oh, because all of those things are empty. So it's essentially just showing that unnecessary thing. Okay. But anyway, we'll just ignore that for now. Okay. Now I am inserting BST dot insert. Let's say 1. Let's see how it goes. And all right. Can I just define one more REPR here so that it automatically. Okay. Yeah. So yes, you can see here that we are able to add 10 to the left and 12 to the right. Okay. Is there a better way to do it? So I'm saying indent followed by this. Okay. And then this L. And then where is the indent? Okay. Oh. I'm just thinking what else can be done. Should I put one more indent here? New line? Oh, I need indent here. Yeah, I need indent here. Okay, I need indent here. So how would you want to do it? Okay, I'm saying indent All right, indent. Then indent and then, okay, indented, then indented, and what is my root value? I'll say value. Then followed by this is a new line, and I'll mark left. No, I'll say indent and would put plus for the left hand side, and then would say left string, and then would put new line, then again indent, then minus. Minus is for representing the right. Okay, or let's just say asterisk. Okay, asterisk is right, plus is left. Okay, would it look okay now? Presentation takes all the time. Where is Val? What did we do? Where am I? Here, right? Here. So I'm saying indent, value, new line. Okay, wait. I have to do self dot value, right? Yeah, I have to do self dot value. Yeah. So 10, and then we have this. Okay. And left string, right string. Okay. So 10, 1 goes in left, 12 goes in right, and like that. Yeah, this is better. Okay. All right. So this is where the recursion gets tricky. And yeah, imagining where is the space going to be, that is something took me some time, right? So 10, the left-hand side is 1, right-hand side is 12. So you can also try inserting more elements. Okay, 11. And can you guess where will this 11 go? Right now we have 10. 10's left side is 1, right-hand side is 12. So 11 would go to the right of 10, but it's already filled with 12. So it'll go to 12's left-hand side, right? So you can see 12's left-hand side. Yeah. Are you guys okay with my presentation? Plus means left and asterisk means right. Okay, everyone?
Yes, Sandeep.
All right, perfect, perfect. And yeah, this way we can keep on adding things into. Okay, so I just added 13. So 13 got added to the right of 12. Okay, and I can insert, let's say, 3. Where will the 3 go? 3 will go to the left of 10. Okay, which is here and so on. Left of 10, so which is 1. 1 is already filled. So it will ask 1 to add 3. Then it'll insert to the right hand side. Okay, so you can see the whole strategy of binary search tree is basically coded in simple code here. See that? All right. So all we are doing is if the value is less than the current value, okay, check if the left-hand side exists. If it doesn't exist, then set the current node. Otherwise, insert to the left. This is where the recursion is happening. Okay. Here, if the value is greater than or equal to the val, right, then insert it to the right-hand side. And while inserting on the right-hand side, if the right-hand side is none, just set it here. Otherwise, call the insert method. Is this code okay? Okay. And who can help me with find? Define find. Find should return the address of the node where the value is found. Okay. So self, and we are searching for the value v. Okay. Who can help me with the code? Find.
So first we will compare with the root.
Okay. We'll say self dot value equals v. Okay. Return self. That's the address of the current node. Okay. Else.
If it is less than value, then it will go to left.
Okay. All right. Now we can go to the left, right? But there could be a scenario if self dot left equals none, right? We'll return none. Otherwise, we will return self dot left dot find value. Correct? Okay. Else search on the right hand side. Okay. If self dot right equals none, return none, as return self dot right dot find value. Okay. So now we can try just searching in this. Okay. So we can also define a method in the BST here. Okay. When somebody says define find, notice that there is a a bit of duplication of the code. So there is a entry point BST and then there is a node. Okay. So wherever I'm needing the recursion, I'm putting that in the node, and some methods I would be putting in the BST. Okay. So I'm saying find. Okay. If self dot root equals none, return none, else return self dot root dot find value. That's all. So I have just created a tree. Okay, this is my tree right now. And now I can say bst dot find 14. It will say none. It returned none. Now I'm saying give me 13. So it returned 13. And this is my node n. Okay, so this is my node n. Make sense, everyone? Are you guys okay? Looks simple, right? Looks simple, right?
Yeah, it's mainly just recursion which is taking it forward, right? Like the
Yeah.
whole steps. It's primarily just recursion.
Yes. All right. Okay. So now comes the time of deletion. Okay. So, all right. I'm leaving this hard question to all of you. Okay. Implement delete. Okay. Question. Implement deletion in binary search tree. Okay. Will you give it a shot? Take a look at the animation. Take a look at the animation. Then how does it work? Let's say I want to delete, let's say element number 10. Okay. How will it do? All right. Okay. What was the name? July 13. Okay. So this is the question that I'm leaving to all of you, and you can try it out. It could not find, so it stopped. Okay. All right. Is everybody comfortable? Yeah. So that's pretty much from my side. You can ask any questions you have. Okay. Those who are wondering where we use these kind of things, know that database uses modified version of binary search tree. When we say we are doing insert, delete, find, this, that, it uses a modified version of binary search tree, which is called as B plus tree. Most of the databases use B plus tree. Okay. B plus tree is nothing but the top elements, first few elements in the tree are kept in the memory, bottom ones are kept in the disk. Okay. That way.
Sandeep, in possible, can you also help us to go through graph?
So we'll discuss that part. So in graph, what is needed, what you need to know is three things. Okay. In graph, you need to know breadth first search, depth first search, and topological sorting. All right. Those three things, and that should be more than enough. Breadth first search, depth first search, and topological sorting. Okay. I'll walk you through that. All right. All of these ideas that you see and hear here, these ideas actually come in very, very handy when you are solving hard problems. Okay. I very well remember in one of my projects in the beginning of my career, right? I used to hear a lot of criticism about computer science in general, that where do we use all that data structure, this, that, and I keep on hearing from many people from industry that where do we use these things? Where do we use these things? The reality is that the problem that you'll see in industry would not tell you that you are supposed to use a data structure. The problem comes in a very, very ugly format. Okay. So I remember very well that my one of like super senior people from my team at DE Shaw, they were trying to implement a simple query language. Okay. They created this thing called document search system, where you will give just like in Gmail, you give the filters. Similar to that, you give the filters and it'll search and give you the results. It looked pretty simple at first, but the moment you see in a query language, you say A equal to 10 or B equal to 20, and then bracket, then and all of that. The moment that thing starts, it becomes completely difficult to solve. Okay. So they were all thinking that they can just do simple string processing and get it done. But in spite of like 20 iteration, they could not do. Okay. And then I was just sitting next to them and I was hearing the entire thing whole day. All I did was I just sat down and just wrote the recursive parser, the one that I showed you today, using the same technique. Afterwards, they could not find a single bug in that. Okay. The beauty of the recursive code is if it has single bug, you'll spot it quickly. Okay. Because same line of code is traversed 100 times very, very much, right? And if there's a minor mistake, you can just quickly spot it with a couple of examples. And then once you basically, I mean, I coded once, there was no bug. They kept on trying for all kind of permutations and it worked fine. And that solved the problem. So it just required, say, 2 hours of my time sitting down and just coding it up because I have solved similar problems earlier. So for me, it was easier. It was very obvious that these things cannot be solved the way they are solving. This need to be solved by the way of proper parsing the data. Okay. And essentially, this is the hardest part of thing. Okay. So knowing all of these upfront helps you solving industry problems. And this would make you super powerful because you'll be able to see the pattern. Oh, this is a recursion. We can just do it this way. Oh, this looks like you can represent it using a binary tree and we can do that. And you will be able to spot that situation. Okay. And yeah, you'll find it very useful. I can guarantee. All right. And of course, as a side effect, it'll be easier for you to crack job interviews because many good companies ask these questions. Okay. All right. Maybe for a data scientist, they won't ask the question, but for, let's say it's a machine learning engineer role or a simple software engineer role in ML, they might ask you these questions. Okay. But I mean, it doesn't harm, right? To be a good problem solver and to be able to clear most of the interviews, it always helps. Okay. And these are the simple commonsensical thing. In normal life, if I give you the same thing, you'll be able to do it like manually, physically, sort the numbers, put this here, like in kitchen, right? In kitchen, you do like hundreds of optimization, right? Like keep all the things that are commonly used on the near to the stove and other things farther, and you basically do all that optimization. And that optimization is what we do in the computer science with all these tree structures, B tree structures, and so on. So the things that we do like normal life very quickly, in the computer science, we do it using these data structures, right? It is like arranging your kitchen. Things that are very, quickly needed, we arrange them nearby, and the things that are far needed very rarely, we keep them away. So designing that structure is called the data structure. Okay. So yeah, I hope this is useful to you. All right. Thank you, everyone. Have a good day.
All right, Sandeep. Thanks, yeah.
Thank you.
It's good,
Thanks,
but
Sandeep.
we'll take time to put heads around it. Yeah, I'll practice this week. Yeah, bye.